Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
In this video, we're going to be discussing the topic of infrared spectroscopy. So this is a type of molecular spectroscopy, which is a study of which frequencies of radiation are absorbed or emitted by a particular substance, and the correlation of these frequencies with details of the molecular structure itself. And so in this case, the infrared region of the electromagnetic spectrum is shown here. And so this is the region of interest that we're going to have for this particular video. Now, infrared spectroscopy provides a direct method of detecting certain functional groups in a molecule. Now, this form of spectroscopy depends on the absorption of infrared light in the wavelength range of 2.5 times 10 to the minus 6 to 2.5 times 10 to the minus 5 meters by vibrating bonds within molecules. Now, in its most general form, the absorption of energy in the form of electromagnetic radiation causes an atom or a molecule in an energy state E1 to change to energy state higher in energy E2. Now, for infrared or IR spectroscopy, what happens is that covalent bonds change from a lower vibrational state to a higher one. Now, radiation in the IR region of the spectrum is most commonly referred to by its frequency in wave numbers. So wave numbers, shown here on the left, is the number of waves per centimeter with units of centimeter to the minus 1, where this is read as reciprocal centimeters. The frequency in wave numbers is the reciprocal of the wavelength in centimeters, or the frequency in hertz, divided by c, which is the speed of light. Now, given the wavelength range that I just previously identified of 2.5 times 10 to the minus 6 to 2.5 times 10 to the minus 5 meters, when expressed in frequencies, the vibrational region of the infrared spectrum extends from 4,000 wave numbers to 400 wave numbers. Now, an advantage of using frequencies is that they are directly proportional to energy. So the higher the frequency, the higher the energy of the radiation. Now, the figure shown here is an infrared spectrum of 3-methyl-2-butanone. The structure here is on the right-hand side. Now, the horizontal axis at the bottom of the chart is calibrated in frequency, or wave numbers. Now, the vertical axis, on the other hand, measures the transmittance, or the fraction of the light that is transmitted, with 100% or 1 at the top and 0% or 0 at the bottom. Thus, the baseline for an infrared spectra, or 100% transmittance of radiation through the sample, or 0% absorption, is at the top of the graph. And absorption of radiation corresponds to a trough or a valley. Now, even though these are conventionally displayed pointing downwards as these valleys, we refer to them as peaks nonetheless. Now, chemists pay most attention to the region from 4,000 wave numbers to about 1,500 wave numbers, because the stretching and bending vibrations for most functional groups are found in this region. Vibrations in the region from 1,500 to 400 wave numbers are more complex and far more difficult to analyze, because even slight variations in molecular structure and absorption patterns are most obvious in this region. It's often called the fingerprint region. Now, if two compounds have even slightly different structures, the differences in their IR spectra are most clearly discernible in that region. Now, atoms joined by covalent bonds are not permanently fixed in one position, but rather undergo continual vibrations relative to each other. Now, the energies associated with these vibrations are quantized, which means that within a molecule, only specific vibrational energy levels are allowed. The energies associated with transitions between vibrational energy levels in most covalent molecules correspond to frequencies in our IR region, or the 4,000 to 400 wave numbers. For any molecule to absorb this radiation, its vibration must cause a periodic change in the bond dipole moment. If two charges are connected by a spring, a change in the distance between the charges corresponds to a change in the dipole moment. In general, the greater the bond dipole, the greater the change in dipole moment caused by a vibration. So any vibration that leads to a substantial change in dipole moment is said to be infrared active. The greater the change is, the more intense the absorption will be. Now, covalent bonds whose vibration does not result in a change in bond dipole moment, for example as a result of symmetry in the molecule, are said to be infrared inactive. So the carbon-carbon double and triple bonds in symmetrically substituted alkenes and alkynes, for example, as shown here below, do not absorb infrared radiation because vibration does not result in a substantial bond dipole change. So these two molecules, the 2,3-dimethyl-2-butene and 2-butyne, are IR inactive. The analysis of the modes of vibration for a molecule is very complex because all of the atoms contribute to the vibrational modes. However, we can make useful generalizations about where absorptions due to particular vibrational modes will appear in an infrared spectrum by considering each individual bond and ignoring other bonds in the molecule. The simplest vibrational motions in molecules giving rise to absorption of IR radiation are stretching and bending motions. So let's consider this for a simple methylene group. What we have shown here are fundamental stretching and bending vibrations for this group. Under stretching, there is symmetric or asymmetric stretching, and two examples of a bending vibrational mode are scissoring or rocking. Two other examples that you might find in your textbook are wagging and twisting, bending molecular vibrational modes. So these are the most typical molecular vibrational modes that you'll see and try to identify when looking at and analyzing an IR spectrum. The most important thing to remember here, though, is for each of these vibrational motions, you have to make sure for the molecule to be IR active, you have to have a change in the molecular dipole moment as a result of this periodic vibration. Now, as a simplifying assumption for an exercise, let's consider two covalently bonded atoms as two vibrating masses connected by a spring. So the total energy is proportional to the frequency of this vibration. So the frequency of a stretching vibration is given by this equation, which is derived from Hooke's law for a vibrating spring. Now here, this first term on the left-hand side of the equation is the frequency of the vibration in wave numbers, which we derived earlier. K is the force constant of the bond, which is a measure of the bond strength in dynes per centimeter, and mu is the reduced mass of the two atoms. Now this reduced mass is m1 times m2 over m1 plus m2, and m here is the mass of each of the atoms. Force constants, or the K here, for single, double, and triple bonds are approximately 5, 10, and 15 times 10 to the 5th dynes per centimeter here. And so this approximately has the ratio of 1 to 2 to 3. So again, just so you see here, the 5, the 10, and 15 for single, double, and triple bonds. So using this value of the force constant for a single bond, we can calculate the frequency for the stretching vibration of a single bond between carbon-12 and hydrogen. So we want to calculate the frequency of the stretching vibration for this single bond. So we can first calculate the reduced mass, and so here we have 12 times 1 over 12 plus 1. Here where the 12 is the mass of the carbon atom and 1 for the hydrogen. Plugging into the equation that I showed you previously for K using the force constant for the single bond of 5 times 10 to the 5th, plugging in mu, the reduced mass here, and the 4.12 in front, we end up getting this frequency of 3,032 wave numbers. Now the experimentally determined value for the CH stretch is about 3,000 wave numbers. Given the simplifying assumptions made in this calculation and the fact that the value of the force constant for a single bond is an average value, the agreement between the calculated value here and the experimental value is remarkably good. So based on this derivation from Hooke's law, we can predict the position of the absorption of a stretching vibration in an IR spectrum, and we can show that that depends on both the strength of the vibrating bond and on the masses of the atoms connected by the bond. So the stronger the bond is and the lighter the atoms are, the higher the frequency of the stretching vibration will be. The intensity, on the other hand, of an absorption will depend primarily on the change of the dipole of the vibrating bond. Well, let's do another example. Calculate the stretching frequency in wave numbers for a carbon-carbon double bond. Now let's assume that each carbon here is the most abundant isotopes, or C12. Also, because we have a double bond here, we're going to assume that our force constant is 10 times 10 to the fifth dynes per centimeter. Plugging into the equation that we derived from Hooke's law before, we have the force constant here on top under the square root over the reduced mass here, 12 for both of the carbon atoms. And this gives us a value of 1,682 wave numbers for this vibrational stretching frequency. Now, based on our assumptions here, this value is pretty close to the experimental value, which is approximately 1650 wave numbers.